And first, just a little review. Saw this already, but this is effectively how we're partitioning the space, the output space for categories when we're looking into multiple layers. Now, in this case, we're assuming that the output is distinguishing something between yes category or no category. So there is effectively a single output neuron. In fact, you know, the output is actually on the top. I don't know in these networks. So if you have a network with 2 neurons, you can have one separating hyperplane. This is larger than that. You cut it once. If you have one hidden layer, you can have the combinations of how many hyperplanes do you have here? 1, 2, 3, 4, 5, 6. So see if you can see why you actually have here a little hexagon from this structure. And you can then create non-convex separating planes if you have higher sets of layers. Now, in this case, we have a threshold function, and the activation units are rectified linear units. That's why they're sharp like that. In the interest of time, in the interest of telling you a little bit more about recurrent neural networks, I am going to skip all of the important things here, such as, you know, things that you already saw in 3 blue 1 brown. See it again, like gradient descent, gradient descent, gradient descent with momentum, backpropagation. Understand, be able to compute backpropagation with any given function. You're going to be happier after that you did. I mean, like if you don't done this by hand, but it's something that is laborious, but also insight-laden. Overfitting is something that reoccurs in multiple different walks of life in machine learning and neural computation. So I'm not going to go into it. If you didn't before. It's also something that it was a potential project, of course. One thing I did want to talk about is the curse of dimensionality in the sense of training data. Right now we had the training data. Say we had like 50 points for 2 categories, 25 category A, 25 category B. And that's nice. I mean, you have 25 examples of a certain category and 25 examples of another category. Now, in general, the number of examples that you need to tune a network grows very fast with the number of different categories you want to obtain. I want to give you an intuition why that is. So for many of these feed-forward neural networks, there's a lot of weights you're tuning, hundreds of thousands of weights. So you need to backpropagate. You want your gradient descent to be on a smooth surface, and so you want to sample that surface with as many points as possible. So ultimately, you want to be dense on your input space. You want to be representative. In a 2-dimensional case, like in the playground, in TensorFlow, it's easy. But in 3 dimensions, it becomes hard very quickly. I wanted to bring you an example of I've never seen this particular data set trained, but I wanted to discuss with you an idea of a complex data set to train on. Okay, so the problem in psychology. Let me go here to QuickTime. So I don't know if you knew, there is a categorization of the personalities on the basis of introspection and extroversion, and basically 4 different features, dominant or non-dominant, that you can frame people in. So I think I forget what the name of the categorization is, but maybe it's Waldorf. I have to check. I'll put it in the links later. But that notwithstanding, the idea is that if you have 4 yes or no dimensions to recognize a single human being, you basically, a human being will become a matrix, or a vector, in fact, where you have like these 4 dimensions, A, B, C, and D. And you can basically be a 1 or a -1 in any of these dimensions. So if you have, say, 4 possible categories you can ever fall in. So this is you know, if you are a Pythagorean Pythagorean, you will be a sanguineous person, or what's the word? Sanguineous, choleric, melancholic, or phlegmatic. So these are the four categories of personalities according to Socrates. This was the old system there. So if you have only a system with four categories, and you can be one of them, then basically you can represent this with four numbers. But this system that I want to tell you about has 16 possible human classifications, okay? And the problem that I wanted to construct is the following. So you have a male, and he is one of 16 outputs. And you have a female, and she is another one of 16 outputs. So she's one of these 16 categories. So this is an example of a 4 category, but I want to talk about 16 categories, because this is what is used now in modernity to frame us. And if now you want to see if a female of a certain category will jive with a male of a certain other category, you basically need a matrix where you will have male types here from 1 to 16, and the female types here. Or it doesn't need to be male or female. Any couple will do. But let's presume male and female for the moment. And say you have a person that is introspective, gentle, and but also blah blah blah. And that person is here in this category. Then you have another person here that is in this other category. So this is one data point of this 16 by 16 matrix. Now we want to find out whether people jive together. So we have to find a sample of humans out there in the world that are in a couple, and we want to see what's the likelihood that they're going to stay together or not. And so we're going to measure whether they're together or not as a function of what are the two categories. So we're going to basically say, okay, so these categories here jive together, and maybe these categories here don't jive together. People that break up relationships, people that have pathological relationships. People have tried to measure this for couples, and there are statistics. And so to obtain these statistics, you need, actually think. Say you want to now sample this space. You will need at least 256 examples of combinations between two different people. And you would like your statistics to be sufficiently powerful, so you want for any category at least, say, 10 examples of people or couples, 10 examples of couples, so that you can have a good balance. Maybe say this combination here is a 50% combination. So from 10 couples, 5 couples didn't jive, and 5 couples did jive together. Now let's add another dimension to that problem. Let's say that a child from a certain couple becomes a certain personality type. So you have a projection of this space onto a single other dimension. That's the child. And you want to know what kind of child will come out of a certain couple type. How many children do you have to sample to be able to have representative categories for all of the sampling space? In principle, every single combination can have 16 more children. So ultimately, you get a cube of 16 on its side with an negative dimension. So whereas for 2 dimensions you needed basically 256 categories, now you have 256 times 16. All right, do that calculation. So it's 1024, 4096. So what I'm trying to get across is the fact that now to sample the population, you would need, say you want 10 samples of every single combination. there's probably going to be a very sparse space out there. Very quickly, you're going to need a whole lot more people to have sufficient training categories to be able to predict on the basis of the parents what the child is going to be, right? Or even if the child's going to be successful in life, now what kind of person is the child is going to meet in the future? Can we predict then? So which kinds of people does the child then search for? Right? So you add yet another dimension. So you have 16 times 16 times 16 times 16. And very quickly to sample that space in the world out there becomes almost nigh impossible. So this is the curse of dimensionality in a relationship example, in a metaphor I've construed. And I forgot what the name of the category is. I should actually give you a little bit more in-depth idea. But, you know, if they're 1 of 16, male, female, 2 times, 3 dimensions, 4 dimensions, very quickly explodes. The idea here is that, actually, there are more metaphors. There are metaphors about darts in multiple dimensions. But the sampling a one-dimensional space is easy, as we saw in the one we just had now. Sampling a 2-dimensional space is also relatively easy. So, sampling a 3-dimensional space, you need many more examples to be able to look into that search space. And now if you think about pictures, let's go from our example that we had from personality categories that jive together. Let's think about all of the possible combinations of 256 by 256 pixels. Let's keep it simple. Let's think about exclusively gray values. So say you have pictures of 250, oh, actually that's a problem in my graphics card. So you have now 256 pictures by 256 pictures with gray values. And this is just a sample of that data space. Now think about what is the size of the space of all possible pictures. It's basically 256 times 256 times 256. You know, it's a big number. So 200 times 200 would be 40,000, times 200 is going to be 160,000. I'm not making some faux pas. Quickly, you in order to sample all of that space, you were going to be running out of memory space. And most of your pictures are going to have nothing in them. I mean, if you want to classify all the pictures, so these are examples of and you will not guess it, but every single one of these pictures has been constructed from a set of faces where you take randomly a pixel from a different picture every time. So basically, these are all pixels that exist in specific faces that, when combined, mean nothing. The main idea here is that when we have these immensely large input spaces, the actual meaningful data is of much lower dimensionality. That's the idea of manifolds. What we just had before here, this is the data set of faces from which those pictures that I just showed you with random picked pixels are constituted from. And you can see that there's a lot of structure between them. So you can then obtain the invariances of them once you have these smaller subset of all of the space of the possible. And this is why networks are effectively competent at classifying data, even if the input space is super high dimensional and we're cursed by dimensionality. It's because the effectively meaningful space is a small subset of all possible combinations. And so this is the idea that topological, lower dimensional topological manifolds is what a network is learning. So that is what you see in the output of the playground that I had. Actually, I think it's even running in the background still. What you see in the output of the playground is the manifold that has been selected from that convoluted space. And that's why you can train it. If you had only random points, if you only give noise and then you assign them labels, it's impossible. Think about that, right? So like if you have just, if your two categories were just noise, and you, then in order to classify them perfectly, to do overfitting, if you like, would require as many neurons as would be sufficient to partition all of your input noisy data set. Can't do that. So that's why our problems are usually of much lower dimensionality, or categories. Points are clustered in different places of the input space. And so this is then the idea that you have a much lower dimensionality in the input space. And that's what, for example, autoencoders exploit. You might have heard this word before. And now I'm going to tell you a little bit about certain architectures, well, basically two, autoencoders and generative adversarial networks, which are feed-forward networks that are also convolutional networks that are attempting to solve for some specific problems, and can do because the dimensionality of the output manifold is very small. So an autoencoder has this structure. It basically is a feed-forward network where the output should be identical to the input. The loss function is not a categorical function. It's not basically whether it fits or does not fit in a category. What an autoencoder is trying to do is you give it a picture and you want the output layer to give you the exact same picture. You start with random weights and you train it. You train it with a loss that compares the input with the output. If in the beginning your output is random because your weights are random, your gradient is going to enforce a certain, your gradient is going to enforce that the weights are trying to copy that certain picture. Now imagine you put a lot of pictures here on the left side of the autoencoder, and for every one of them, you have a loss for that output. Turns out that these networks, you might think, what's the gain of that? I mean, you know, just copying from left to right, you're finding a network that is the identity transformation. The gain of that is that because the input space of picture is a small space of that input manifold, you are able to represent pictures with a much smaller input set than the entire number of pixels you had in the left place, in the left side in the first place. So here you see that in the autoencoder you have a convergence to the hidden layer. The green neurons are the hidden layer neurons, and what they're doing here is they're combining from the input and mapping to the output with many fewer neurons, thus compressing the input space. You can then use this for cryptography, for example. If you train an autoencoder and you give to the other person just the hidden layer, you can give them a representation of the output of the picture you're going to get on the output that is of much smaller size. See if there's questions here. So this is one way in which you can use these autoencoders or feed-forward neural networks to reproduce pictures by creating a latent representation. In fact, latent representation at the hidden units. And so you can use that to transmit information, and you can use that to denoise pictures because of these characteristics of the lower dimensional manifolds. So this is a line autoencoder. I'm going to skip that. Generational adversarial networks is how you make deepfakes. If you didn't know, they're very cool. So the idea is that you have an autoencoder that in the output, your loss function is something that you have to define your output function as to be something that you would like to see in the other end. So you put a picture of Obama on the left, and you take a picture of Trump on the other end, and you create a loss that says, okay, when you put a picture of Obama, give me a loss unless I produce a picture in the output layer that looks like Trump, just to give you the sense. So this is a style transfer network that is a generative adversarial network. It wants to transform photos into Monet-looking pictures and vice versa. You want to transform zebras into horses. So how do you train this? How do you train the GANs? How do you basically create these loss functions? And so that's my GPU problem again. You create two networks, a little bit like autoencoders, where you have a generator network that takes something, random input, and has to produce something that looks like what you want in your output according to your loss function. And you have a discriminator network that attempts to tell whether generator examples fit into the category you want to observe in the end. And you jointly train them. You jointly train with this. Here is the example of the set. So if you have random noise into the generator produces a fake image because we have a training procedure that makes the generator produce pictures from random noise. So you give random noise, but because the loss has specific features, a fake image is produced. Meanwhile, you have a training set of real pictures that have the feature you want, and you give the two to this discriminator, which just basically outputs a categorical value of either it looks like what I want it to look, or it doesn't look like what I want it to look. So you have these two networks, the generator network and the discriminator network, and they're trained independently to discriminate whether pictures have zebras, and the other one to produce zebra pictures. The moment then you start to give to the generator network not random noise, but a horse, it tries to, via its weights, infuse some zebra-ness into the horse. And so that's how generative adversarial networks look like. And that's, if you don't have a random input, but you have maybe labels. Okay, so I want a window where it is, an open window is yellow, a closed window is blue, a terrace or saccade is green. This pix-to-pix software that implements GANs, generative adversarial networks, produces an output that looks believably like the input that had been trained on. So the generator can then produce window-looking greens. And the better you discriminator picture, the better you can create deep fakes. You can also do this over time. It's not easy to train again. And I'm not going to go into this in the detail, but you have problems like mode collapse, evolution speed difference between the discriminator and generator, and so forth and so on. Have a watch. If you're curious about this, have a watch into an entire GAN talk about 1 hour, and then they were going to break this into multiple more pieces that I haven't discussed. But I would like you to then at least have a sense that, training networks is a little bit of an art, and so this is how the art is. Okay, this ends the feed-forward neural network part of our course. Now I want to bring us to recurrent neural networks, where I will have the opportunity to talk about some different aspects of what recurrences can add to our understanding of how the brain works. In fact, feed-forward neural networks can be criticized against the brain in many ways. Recurrent neural networks also, but they also have other metaphorical values. So I think we won't have the time to go into reinforcement learning, but reinforcement learning is basically do more of what makes you happy. So if you like the reinforcement learning, then you should just go and do that because it will make you happy, and then you can do more of that, and so forth and so on. You can have policies like that. But let's not go there today. Let's go to recurrent neural networks. I'm going to pause this recording for a moment to start it again, just because it's going to be easier.